Welcome to our quantum deep dive. Today we're plunging into a topic that sits right at the cutting edge, the point where quantum computing and artificial intelligence collide. Specifically, we're looking at something really fascinating called quantum-assisted feature selection. And our map for this journey is an insightful essay by Jörg O. Schneppat titled Quantenunterstützte Merkmalsauswahl für optimierte KI.
That's right. And if you work with AI or, machine learning, you know that feature selection is just fundamental. It's that crucial process of sifting through all your data points, all the potential features, and figuring out which ones actually matter most for what you're trying to predict or classify. Now, classical methods for this are incredibly valuable. They're the backbone of AI today, but they really run headfirst into some tough limitations, especially with the sheer volume of data we have now. And this essay explores how quantum computing might just offer a way around those limits. Our mission, really, is to pull out the core ideas for you.
Okay, so let's unpack that challenge first. Feature selection. Imagine you've got this massive spreadsheet, maybe thousands of columns wide, but you only need, a handful of those columns to actually figure out what's going on. Feature selection is finding that critical handful, right? Picking the best, most relevant features, ditching the noisy ones.
Exactly. And here's where it gets really hard for classical computers. If you have n potential features, the number of possible subsets you could pick is 2 to the power n. Just think about that. If you have just, say, 100 features, 2,100 possibilities, that number's just astronomical, bigger than atoms in the universe kind of thing. So finding the absolute best subset means searching this enormous space. And that quickly becomes what we call an NP-hard problem. Classical machines just can't check all those options efficiently once n gets even moderately large. They just don't scale.
Right. That exponential growth is the killer. And if you don't get feature selection right, the downsides are pretty big, aren't they? Keeping too many features makes your AI model slow, eats up computing power, but it also makes them prone to overfitting.
Yeah, that's a big one, where the model just learns the training data, noise and all, and then fails completely on new data it hasn't seen.
Plus, bloated models are just black boxes, right?
Yeah.
Hard to interpret why they made a decision.
Absolutely. And the essay mentions how classical ML has tried to tackle this, acknowledging the trade-offs. You've got filter methods using simple stats like correlation before training, fast, but they might miss how features interact.
Okay.
Then wrapper methods, which use the model itself to test subsets, like forward or backward selection. They capture interactions, but wow, they are computationally heavy.
Right, training the model over and over.
Exactly. And embedded methods like lasso, build it into the training, clever stuff, all of it. But, as the essay points out, they all eventually hit that wall, that combinatorial explosion, especially with really complex data where feature interactions are key.
So the core problem is this huge optimization challenge, finding that needle in the second haystack. And this is where quantum computing enters the picture. What's so different about it? What makes it potentially better for this kind of problem?
Well, it really boils down to using some fundamental quantum principles that classical machines just don't have access to. First up is superposition. You know how a classical bit is either 0 or 1?
Right, binary.
A quantum bit, a qubit, can be in a combination, a blend of both 0 and 1 at the same time. It's like existing in multiple states at once. So a bunch of qubits can represent and sort of process many possibilities concurrently.
Okay, multiple states at once.
Then you've got entanglement. This is where qubits get linked, deeply connected. Their fates are intertwined. Measuring one instantly tells you something about the other, no matter how far apart they are. It's weird, but powerful.
Einstein's spooky action at a distance.
That's the one. And using superposition, quantum computers can potentially achieve quantum parallelism. In a, let's say, simplified sense, one quantum operation can act on all the possible states represented by the qubits simultaneously. It's just a different way to explore these vast computational spaces.
Okay, superposition, entanglement, parallelism. That's the quantum toolkit. But how do we actually apply that weirdness to finding the best features? How does it solve that optimization puzzle we talked about?
Yeah, the key insight the essay brings out is that certain quantum algorithms seem tailor-made for this kind of problem, finding the best configuration among tons of possibilities. It's combinatorial optimization, right?
Okay.
Which is exactly what feature selection is at its heart.
So quantum is good at optimization?
Potentially, yes.
Yeah.
And the essay points to two main quantum approaches being looked at for this. One is quantum annealing. Think of it like trying to find the lowest valley in a really complex, hilly landscape. You map your feature selection problem onto this landscape, different points or different feature sets. The height is how bad the set is.
Lower's better.
Right. A quantum annealer is designed to naturally settle into that lowest energy state, which hopefully corresponds to your best feature subset. This often means translating the problem into something called an Ising model, or a QUBO, quadratic unconstrained binary optimization, basically turning include-exclude feature into a binary choice and finding the minimum cost.
Okay, that's annealing.
Oh, yeah.
What's the other?
The other main type involves variational quantum algorithms. A popular one is QAOA, the quantum approximate optimization algorithm. These are actually hybrid algorithms. They use a quantum computer for part of the calculation, usually running a relatively simple quantum circuit. Then a classical computer measures the result, tweaks some parameters in the quantum circuit, and they go back and forth.
So quantum and classical working together.
Exactly. They iteratively refine a quantum guess to find a good approximate solution to the optimization problem. It combines quantum exploration with classical fine-tuning.
Okay, so we have this super hard classical problem, feature selection, and these potentially powerful quantum tools like annealing and QAOA designed for optimization. How does that actually work in practice? Does the quantum computer just take over the whole job now?
Well, the motivation is clear, right? Quantum computing promises potential speed-ups for these NP hard problems that just bog down classical machines. It's a new way to search that massive 2N space.
But I sense a but coming.
Yes, there's definitely a but.
Uh-huh.
And the essay is very clear on this. The current reality is that quantum hardware, well, it isn't quite there yet. It's not powerful enough today to tackle the full scale of many real-world feature selection problems entirely on its own. Purely quantum solutions for the biggest data sets are still some way off.
So what are people doing?
This is where the hybrid quantum classical models come in. That's the dominant approach discussed in the essay and what you see most research focusing on now. You basically combine the strengths of both worlds.
Okay, how does that look? Walk me through a typical workflow.
Right. So a typical hybrid setup might go something like this. First, you use your classical computer for the initial grunt work, loading data, maybe some basic cleaning or pre-processing. You might even use simple classical filter methods to quickly weed out obviously useless features.
Get rid of the low-hanging fruit, classically.
Exactly. Then you take the remaining, harder feature selection problem and formulate it for the quantum computer, maybe as that QUBO we mentioned. You hand that specific optimization task off to the quantum hardware, a quantum annealer, or maybe a gate-based machine running QAOA. Let it do its thing to find the optimal subset from that reduced set.
So the quantum part tackles the really complex combinatorial bit.
Precisely. Then the quantum computer gives you back its answer, the chosen subset of features. You take those features back to your powerful classical computers for the standard stuff, training your actual machine learning model, evaluating its performance, deploying it. It really leverages the quantum device for what it's potentially best at, that tricky optimization, while classical handles the rest.
That makes a lot of practical sense, using each for its strengths. So is this happening? Are people actually building this stuff, or is it still mostly theory?
Oh, it's very much an active area of R&D.
Mm-hmm.
The essay points to several key platforms people are using. There's IBM Qiskit. That's a big open source framework for gate-based quantum computing, good for things like QAOA. Then D-Wave Ocean, which is specifically for their quantum annealers, really geared towards those QUBO-type optimization problems.
Right. The annealers are built for optimization.
They are. And you also have platforms like Google Circ and Amazon Bracket offering access to various quantum hardware and tools. So the ecosystem is definitely growing.
And where are they applying it? What kind of real-world problems?
The essay gives some great examples. Biomedicine is a huge one, finding the right genetic markers or important features in medical images from massive data sets. Think disease diagnosis, personalized medicine.
Makes sense. Tons of data there.
Exactly. Finance is another, selecting the best features for risk assessment, detecting fraud, or building algorithmic trading models from huge streams of market data. Also, material science, trying to pinpoint the key properties needed to discover or design new materials. And cybersecurity, analyzing network logs to find the few critical indicators of an intrusion really quickly.
Wow, those are all areas where finding the signal in the noise fast is critical. And the potential payoff seems clear. Maybe faster insights, maybe simpler, more accurate AI models down the line because you've picked better features.
That's the hope. That's the goal. But again, the essay is realistic. We're still in the early days. There are some significant challenges.
Okay, let's dig into those limitations then. What are the main roadblocks right now?
The biggest ones, as the essay details, really come down to the quantum hardware itself. We're currently in the NISQ era. It stands for Noisy Intermediate Scale Quantum. Intermediate scale means we just don't have that many usable qubits yet. Maybe dozens, maybe a couple hundred in the best systems. That's often not enough for the truly enormous feature selection problems with thousands of potential features. That seeded space is still too big.
Okay, so scale is one issue. What about the noisy part?
That's maybe even bigger right now. Qubits are incredibly delicate. They're super sensitive to environmental noise vibrations, temperature changes, stray electromagnetic fields. This noise causes errors in the computation. You get decoherence where the quantum state just falls apart. You get errors when you try to perform operations or even just read out the answer.
So the results aren't always reliable.
They can be error-prone, especially for longer, more complex calculations. What we really need for reliable, complex quantum computing is fault tolerance. That means using many physical qubits to encode one error-corrected logical qubit. It's possible in theory, but it requires a huge overhead in the number of physical qubits, which is not there yet at scale.
So limited qubits, and the ones we have are noisy. That sounds like a tough combination. Given these hurdles, what does the essay suggest about the path forward? What's the future look like for quantum-assisted feature selection?
Well, it suggests that for the near to medium term, those hybrid quantum classical models are likely key. They let us leverage what current NISQ devices can do, even with noise and limited scale, to potentially get an advantage on specific subproblems, while classical does the heavy lifting elsewhere. As the hardware gradually improves maybe a few more qubits, slightly lower noise levels, the quantum part of that hybrid approach can hopefully tackle progressively larger chunks of the problem.
So evolution, not revolution in the short term.
Probably. The real revolution, the point where quantum truly transforms feature selection for massive data sets, seems to depend on those big breakthroughs in hardware. We need much larger machines, and crucially, we need fault-tolerant quantum computers. That's the long-term goal for many.
And what about the software, the algorithms?
That's also critical. We need continued development of more powerful, maybe more specialized quantum algorithms. Perhaps algorithms designed specifically for machine learning tasks. The essay touches on the broader field of quantum machine learning people, exploring things like quantum neural networks, quantum Boltzmann machines. These could also play a big role down the line. The long-term vision, really, if all this succeeds, it's about being able to tackle data analysis problems of a scale and complexity that are just completely out of reach today. It could unlock entirely new AI capabilities.
Okay, so let's pull back from this deep dive into Jurgo Schneppet's essay. We've seen how classical feature selection methods, while useful, really hit a wall because of that exponential complexity with huge data sets. Quantum computing, using principles like superposition and entanglement, offers a fundamentally new way to attack that core optimization problem. And right now, the most practical path seems to be these hybrid quantum classical approaches.
That's a great summary. And despite the very real hardware challenges, noise, limited qubits, it's clear that researchers and companies are actively pushing forward. They're exploring and applying these quantum techniques, often in hybrid ways, in really important areas like medicine, finance, materials science. It really signals the potential impact this technology could have as it matures.
It really does make you pause and think, doesn't it? Think about any field out there that's drowning in complex, high-dimensional data. Climate science, drug discovery, maybe understanding the brain, cosmology. What crucial insights, what breakthroughs might be hiding in that data right now, just beyond our classical computing grasp because we can't effectively sift through it. Could quantum-assisted feature selection, as discussed in Schneppet's work, be one of the keys that eventually helps us unlock some of those profound discoveries? Something to ponder. Goodbye.